All right, let's dive in. Today, we're going to explore a really elegant idea that sits right at the heart of how computers understand language: syntax-directed translation. Have you ever just stopped and wondered how a simple line of code, it's just a string of characters on a screen, how does that actually transform into a real, meaningful action inside a computer? How does the machine go from just seeing text to truly understanding an instruction? That's really the core question we're going to unpack together today.
So where does the computer even begin? Well, the very first step is to see past the text and discover its hidden blueprint. Yep, just like an architect's plan for a building, turns out code has this secret structure that guides everything.
Take a look at this. It's a pretty familiar line of code, right? To us, it's obviously an assignment statement. But to a compiler, when it first sees this, it's just a sequence of characters. A, then a bracket, then I, and so on. It has no real meaning. Not yet, anyway.
So how does the computer figure out that hidden structure? It uses something called a context-free grammar. The best way to think of this is as the official rulebook for the language. Just like English grammar tells us how to put nouns and verbs together correctly, a programming language's grammar tells the compiler how all the pieces, the variables, the numbers, the operators, can be legally combined. And by applying those rules, the compiler transforms that flat line of text into this, a parse tree. Now, this is where the magic really starts to happen. For the first time, we can actually see the blueprint. The code's logical, hierarchical structure is laid bare. This tree, this is the foundation for literally everything that comes next.
Okay, so we have the structure. We've got the blueprint. But a blueprint is just a drawing, right? It doesn't have all the information you need to actually build the thing. So how do we attach actual meaning and instructions to it? Well, that's our next step.
We do it using something called attributes. You can think of attributes as little notes, or maybe sticky notes, that we attach to each and every part of our parse tree. These notes hold all the crucial info, like the data type of a variable, the location of a value, or the result of a calculation. Now, one of the most common types is a synthesized attribute. The key idea here is that information flows up the tree, from the leaves all the way to the root. Imagine you're building something with Legos. The properties of the final thing you build are synthesized from all the smaller pieces you connected below it. It's the exact same idea.
And how do we know how to calculate these attributes? We use what are called semantic rules. You can see one right here. It's a very specific instruction that's attached to the addition part of our blueprint. It just says, hey, to get the value of the expression e at the top, just take the value of its left child, e1, and add it to the value of its right child, t. It's a precise, simple instruction for how meaning gets built. And this illustrates that upward flow perfectly. This is a dependency graph. It just makes it super clear that to get the final value for e at the top, you first need the values from its children, e1 and t. Meaning is built from the bottom up, from the smallest pieces to the whole expression.
Okay, so we can define the structure with a grammar, and we can specify the meaning with rules. But how do we turn all of this into a concrete process? An actual step-by-step translation.
This brings us to two ideas that are really closely related but have one key difference. Think of a syntax-directed definition, or an SDD, as the what. It's the architectural blueprint. It shows what the final thing should look like. The translation scheme, or SDT, is the how and when. It's like the construction schedule. It tells you when to do things, when to pour the foundation, when to put up the walls. The source material gives us the perfect name for these embedded program fragments. They're called semantic actions, and these are the little snippets of code that actually do the work. They're the things that might print a result, generate a piece of machine code, or update a table somewhere. So the amazing thing is that this whole complex-sounding process can be boiled down to just 3 elegant steps. First, we parse the input to build a blueprint, our parse tree. Second, we annotate that tree by figuring out all the attribute values at each node using our semantic rules. And finally, we traverse, or walk, the annotated tree to execute our actions and produce the final translation. Parse, annotate, traverse. That's the flow.
Now, let's just zoom out for a moment and really appreciate the quiet power of this pattern we've just walked through.
Because when you strip away all the details, all the technical jargon, the idea itself is incredibly simple and, honestly, beautiful. You define a formal structure using a grammar, and then you systematically attach meaning to that structure piece by piece, from the bottom up. That's really it. And this simple pattern is why syntax-directed translation is so fundamental.
It's the engine running behind not just compilers and interpreters, but also the static code analyzers that find bugs in your code, and even sophisticated typesetting systems like TeX, which, fun fact, produce the very book this explainer is based on. It's used basically anywhere a formal language needs to be understood by a machine.
So, what's the real takeaway from all of this? You know, when you're learning about compilers or language design, it can feel so overwhelmingly complex. But the key is this: complex systems are almost always built from simple, elegant patterns. If you can focus on this one core idea, first find the structure, then attach meaning, you start to see the underlying simplicity. Because understanding the blueprint is always the first step to becoming the architect.